Hey guys, this video is all about spontaneity and whether or not a reaction is spontaneous. Okay, so a spontaneous process is a process that occurs without any outside interference. That doesn't mean that you can't take an ice tray out of the freezer and put it on the countertop. It just means that once it's on the countertop, you don't have to do anything else to it. So ice melting at 25 degrees Celsius, well, 25 degrees Celsius is above the freezing point, so it would melt. It's spontaneous. A ball is going to roll down the hill. Soda is going to go flat if it's left open. Iron nail rusting in an environment with moisture, it's going to happen. So those are all spontaneous processes. They occur without any outside interference. It can also be called thermodynamically favorable. So anytime something asks you whether or not it's thermodynamically favorable, they're asking you whether or not it's spontaneous, or it has a property of a spontaneous reaction. All right, so to talk about when a reaction is spontaneous, we first have to talk about the second law of thermodynamics. And the second law of thermodynamics states that a process can only occur if they're increasing the entropy of the universe. So the first law is the energy of the universe is constant, and the second law is entropy of the universe is always increasing. Now that's not entropy of the system, it's entropy of the universe. So that's the system and the surroundings added together. We've currently always been calculating the entropy of the system. So the way you would calculate this, the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings. Now we're not going to talk about how to calculate entropy of the surroundings because it's not in AP curriculum directly, but they do want you to know the second law of thermodynamics. There's a different way that we find out if a reaction is spontaneous or not. Since we're not calculating the entropy of the surroundings, we're not technically calculating entropy of the universe. We use free energy to do that, to tell if a reaction is spontaneous. And so if free energy is negative, so if delta G is less than 0, then it's spontaneous. So the entropy of the universe would have to be positive, and that would give a free energy that is negative, and that's of the system. So of the reaction or process that's occurring. Okay, so free energy and spontaneity. So if we use this reaction, we look at this reaction really closely, we can determine if a reaction is going to be spontaneous half the time if we look at the enthalpy sign and the entropy sign. So if it's exothermic, then delta H is going to be negative because it's losing heat. And if it's endothermic, it's going to be positive because it's gaining heat. All right, and in the last video, or 2 videos ago, we looked at how to determine whether or not the sign of delta S was going to be positive or negative. So instead of calculating delta G to see if delta G is going to be negative, we can kind of interpret that. All right, so if I look at this, if I have a negative delta H minus temperature in Kelvin times my entropy, and my entropy is a positive number, then that means this right here, because they're being multiplied together, would be negative, and then we have a negative, and they're being added 2 negatives, and so delta G will always be negative. And if delta G is negative, then that means it's spontaneous, and this will be spontaneous at all temperatures. All right, so then if I look at the next set of conditions where it's the opposite of that, if my delta H is positive and my delta S is negative this time, I have this negative here times a negative, which gives me positive value plus a positive, so this would be positive delta G, and that would mean that it's non-spontaneous at all temperatures, so it could never be spontaneous the way that it's written. Now the reverse reaction would be spontaneous, but this reaction would not, because if we reverse the reaction, the sign changes, and so the reverse reaction would be spontaneous, but the forward reaction would not be. And then next we have positive and positive. So if delta H is positive and if delta S is positive, then negative times a positive would give me a negative, and we have a positive. So this could be negative or positive. So it could be spontaneous or non-spontaneous. The thing that it would depend on would be the temperature. So at high temperatures, this value would be larger in magnitude than this one. And if that was the case, then the negative sign would overpower the positive sign and we would have a negative delta G. So this would be spontaneous, but only at high temperatures. Okay, and then the last one that we have is where they're both negative. So this is negative, and this is negative, and we have a negative times a negative, which is a positive. So again, we have a negative plus a positive. So it could be positive or negative. And this one is going to be spontaneous at low temperatures because we'd want this to be bigger than this piece in order for the sign, the negative sign, to end up in our answer. All right, so you can memorize this table or you can understand how to figure it out, but this will save you tons of time and struggle on the AP test. There's some little tricks that you can remember. So if it's delta H is negative, then that means the surroundings will feel hot to you. So you should feel heat. And then if entropy is increasing, it's getting more messy. So a hot mess is spontaneous. Okay, so a hot mess, the reaction happens. Things are going to turn into a hot mess. That's just the way it's going to work. All right? Cold order does not. It's not spontaneous. And then spontaneous at high temperatures are going to have both of them being positive. So that means up. And then negative, they're spontaneous at low temperatures. So the only one that's non-spontaneous is cold order. So it's positive delta H and negative delta S. And the one that is always spontaneous, no matter what temperature it's occurring at, is a hot mess. Okay, so the first example, using the values provided in the table below, determine whether or not the reactions will be spontaneous. If not, would changing the temperatures allow the reactions to proceed? If so, what temperature would they become spontaneous? Okay, so for A, I'm going to find delta G. So remember the equation, delta G is equal to delta H minus T delta S. So I'm looking for delta G because that will tell me if it's spontaneous or not. And I have to convert all of these to joules, so I have to multiply them by 1,000. So it'd be 315,000 minus, and my temperature needs to be in Kelvin. And so I'm going to add 273 to this, and that's going to give me 320 Kelvin. So that'll be 320 Kelvin times negative 405. And this is going to be negative 315,000 minus negative 129,600. So I get 185,400 joules, or 185 kilojoules. And so since this is negative, this reaction is spontaneous. And the only reason it's spontaneous is because the temperature is low enough, this is low enough to where this gets to carry the sign, right? So like if you have negative 5 plus 3, the sign is negative because 5 has a greater absolute value. So in this example right here, the heat, the delta H, has a greater value right here than this does. And so that's why it's spontaneous, because the temperature is low enough. If this temperature got too high, it would no longer be spontaneous because this right here would end up being positive. All right, part B, delta G is equal to 95,000 minus, and then 12 plus 273 is going to be 285. So I have 95,000 joules minus negative 34,200. So this is non-spontaneous. And it says, if not, would changing the temperature allow the reaction to proceed? Well, it wouldn't, because this is positive here and this is negative, and that is a cold order, right? So it's becoming more ordered, so it's not messy, and it's cold because it's positive. So it's stealing heat from the surroundings. So it would never be spontaneous. Part C, remember guys, these are in kilojoules and these are in joules here, so they have to be in the same units. So that's why I'm converting everything to joules. So delta G is equal to negative 101,000 minus, and this has to be in Kelvin, so that's going to be 279. And this is positive. So here I can already tell that this is going to be spontaneous because I have a negative, a hot mess, right? It's getting more messy. So this is negative 101 minus positive 4380. So I get negative 106,000. And so this is going to be spontaneous, and it's always spontaneous. So if it was just asking whether or not it was spontaneous, you really didn't have to calculate it. So you can just look at this, and I could say, this could be spontaneous. It may or may not be spontaneous. So I'd have to calculate delta G to find out at this particular temperature. So the Kelvin temperature is 525 Kelvin. And I get positive 18,925, so it's not negative, so this is non-spontaneous. But I know that it could be spontaneous if this right here was bigger than this one right here. See, it's still smaller. So I need to make this bigger. So it's going to have to be at higher temperature than 525. But it asks me at what temperature would they become spontaneous. So now if we look at a number line, if this is 0 and this is -1 and this is +1, then this is where that change happens when it becomes negative to positive. And so if this is delta G, down this way they're spontaneous, and up this way they're non-spontaneous. So I'm going to use 0 as my guide for delta G and solve for temperature. So delta G is 0, and that's going to be equal to 115,000 minus temperature, because we're looking for the temperature that it becomes spontaneous at. That's why I put a 0 in for delta G. And then I'm going to subtract negative 115,000 from both sides. And then I'm going to divide by negative 183. So I end up getting, I'm going to bring this over here. And I get my temperature is equal to 628 Kelvin. So temperatures above 628. If this was 628 or higher, I'd end up getting a negative value here. It would change it from positive over here to negative, and that's why we use a 0. Okay, determine if the following reactions are spontaneous under standard conditions. If they are not, will a change in temperature change the spontaneity? If so, would an increase or decrease in the temperature change the spontaneity? All right, so if I look at this reaction, is the entropy increasing or decreasing? Well, the entropy is increasing because it's going from solid to aqueous substances, so my delta S is positive, and then my enthalpy is negative because it's a product, which means my delta G will always be negative, and this will always be spontaneous no matter what, because it's a hot mess. All right, so in this one I have a positive delta H and a negative delta S. And that's the complete opposite of what is above. So this one is never spontaneous. In this one, my delta S is negative and my delta H is negative. So both of these are negative, so that means that this is going to be spontaneous at low temperatures. All right, so I know because they're both negatives. Negative is low. That's how I memorized it. If they were both positive, it'd be at high temperatures. All right, and then the last two are examples of calculating boiling points or melting points. So remember, a boiling point or melting point is at the place on the number line where it becomes spontaneous. So we have delta G here at 0. We want it to be down here, not on the other side. So I set my delta G to 0 and solve for temperature. So that's exactly what I'm going to do here. So I have 0 is equal to 40,680 joules, because this is in kilojoules, so I have to multiply by 1,000, minus temperature is what I'm looking for, times 109. So if I rearrange this and subtract 40,000, I get 40,680 joules. It's going to be equal to negative 109 times temperature. I'm going to divide by negative 109 on both sides. And I end up getting that my temperature is 373 Kelvin. And this is water. 373 Kelvin is 100 degrees Celsius. So that's exactly what we expect. Okay, and then ammonia, the enthalpy of fusion is 58,051 joules per mole, and the entropy of fusion is 28.9 joules per mole Kelvin. Will ammonia spontaneously melt at 200 Kelvin? What is the approximate melting point? So I'm just going to solve for the melting point and see if 200 Kelvin is enough. So I end up getting negative 58,510 is equal to negative T times 28.9, divide by negative 28.9, and my temperature is 202 Kelvin. So this is not quite high enough. It would have to be 2 degrees higher. All right, that's it. Good luck.